All right, so my intent, let me start video here. Boy, I've got hat hair. That's not great. I'm going to run this the same way I would have run had we been totally sort of remote. I'm going to ask you guys if there's things that you'd like to do. And what could be helpful is to sort of go through, I have my iPad here because I was going to go through some of the questions that were on sort of that very lengthy sort of study question, a set of study questions that were just from like old exam questions. So if you have a question on something, we can sort of maybe pull it from that to sort of go over. But I'm just going to open it up and ask you guys if you have questions on stuff. I'm going to actually share my iPad here so I can pull that up. Questions? While I'm pulling this stuff up, feel free to just kind of.
We do some PV and RT stuff.
PV equals NRT stuff. Yep. So I will look at the one question that we sort of have that's on this sort of study guide, and then I'll highlight some other sort of examples of questions and maybe even go back to some previous stuff. So let me pull that question up here. And then I'll share my iPad. How you guys feeling about naming? Okay. So I'll start here. Unit conversions is rough. Okay. Lauren, and whenever you are done, if you have questions, I'll pause here for a second and see if you have any questions, but if you're done, then you can just set stuff in my office and roll. Yep. Wow, like this might be close to the entire class here. That's pretty nice. Oh. And sorry, maybe I did not fully communicate that we're going to be in here and not in our classroom space. So what I thought I could do is just sort of go through. So I'm recording this too, but then you guys can kind of see what I'm projecting on my iPad up here. Tell me areas that you're feeling like a little fuzzy on, and we can both look at some of the practice questions that we have here from these final exam practice questions. And then also maybe go back and look at previous quizzes or things like that to just kind of remind you and show you examples of problems like that. So the first thing that was brought up was gas law stuff and PV equals nRT, right? So there's a couple of questions here that asked to think about sort of some qualitative pieces. I just had them here. So where are they? Again, this part was just asking you to remember, like, these are all units that we have of pressure. So 1 atmosphere is equal to 760 torr. Torr is one that's not on here. We really didn't see this as much, but pascals and millimeters of mercury are other ways to think about gases. Big thing that students tend to do that's kind of a mistake is they use PV equals nRT when they don't have a gas. Okay, so two common mistakes that people will make when they're doing something with PV equals nRT. N has to have units of what? Moles. N has to be moles. So common first mistake that students do is they just understand that N is a quantity, but they'll put in grams or whatever pieces. Has to be in moles. And then another common mistake is that people will use a quantity that's not a gas in PV equals nRT. Because maybe you're doing a stoichiometry problem and PV equals nRT is a way to walk to moles if you know the pressure, the volume, and the temperature of a gas. But maybe they'll be actually using, the grams of something that you started out with that wasn't a gas and put that into PV equals nRT. And you have to change who you're talking about with the balanced chemical equation. So let me look at, there was only one sort of calculation problem here that had to do with PV equals nRT. So I wanted to kind of pull that one up and look at it. So this is sort of a stoichiometry problem that kind of embeds PV equals nRT. And then I'll take a moment and I'll go back and we'll look at maybe some stuff from that unit when we did PV equals nRT and remind you of the other kinds of problems that you could see. So this is a classic example of this kind of a problem where we're using this kind of from a stoichiometry standpoint. So lots of stuff embedded in this problem, right? We're given a chemical formula as words. So we have to take those words, make sure we know how to take those words and make them into chemical formulas, write a chemical equation, and then balance it. So here is our balanced chemical equation for that chemical process. So sort of, you will see problems, particularly at the end, right? Everybody's noticed that I put up on Blackboard page 1 and 2 of your exam, which is just like the resources thing, but it also gives you the instructions to highlight, here's what you need to know how to do. So there's 3 parts to the exam. Part 1 is the stuff where it's basically like no partial credit, kind of maybe multiple choice or things like that, simpler questions. Then I believe there's 7 questions which are like calculation based, which are sort of like this. And then there's a list of questions at the end that are more sort of integrative. And you pick 3 of those that you want to do. So I think there's maybe between 10 and 12 different possibilities, right? One of them's kinetics, one of them's equilibrium, one of them's stoichiometry, right? But you don't necessarily know just looking at that, but you're going to need to look at those lists of questions. You're going to pick 3 of them that you do. Okay. So, but let's continue working through this. So this is sort of a stoichiometry question at its core. So this is asking us if we started with this many grams of propane, and here's our propane, how many moles of carbon dioxide, right? So the kind of map isn't written on here, but if we know grams of this, we can get to moles using molecular weight. We can change who we're talking about using our balanced chemical equation. And then we can get back to, well, actually, this is just asking us for moles of carbon dioxide. So that's sort of our final answer there. So that's our walk that we have there. Embedded in this problem is you needed to be able to calculate a molecular weight. So some of these later problems, they're going to ask you to put those skills sort of together. And here's the gas, Sam, part of this problem, because it says, what pressure of carbon dioxide gas would this be if it's in this volume and at this temperature? So PV equals nRT has 5 pieces to it, but R is a constant, so 4 variables. As long as you know 3 out of the 4, this is what we call one of those unknown variable problems. So you're just solving for what's unknown. So we know the number of moles. We calculated that in the previous step. They tell us the pressure. They tell us the volume, and they tell us the temperature, and we want to solve for pressure. So with gas stuff, this is using PV equals nRT, and it's an unknown variable type problem. Okay, so not part of what we have here, but let's go find one of those problems, is when we had kind of an unknown variable problem. I'm sorry, a changing variable problem. So kinetics, gas stuff was pretty early on. I think it was in unit 2. So it may take me a second to find it here. I actually think it was unit 4. Unit 4?
Yeah.
Now I'm like, wait a minute, it was after we did. Yep, at the very, here we go. So let me see if I can find some lecture notes too that will help us kind of think about it. Okay. So this is going to be a good way to summarize this. There's 2 kinds of problems. We just did one that's an unknown variable kind of problem. So that's using PV equals nRT, and you will always use R in these types of equations because you're solving for one of those other variables. So you need to have the R part as with it. Again, 2 classic mistakes that students will make when they're using this equation is they won't have N as moles. So you have to make sure that it's moles, or they'll try to use PV equals nRT with a substance that's not a gas. So make sure that if you're using PV equals nRT, it's moles of a gas. Everybody good? Second way that you can see this is what we call a changing variable problem. And I know this equation looks really scary, but remember, it's just telling us that we have 4 parameters of a gas that are always going to equal this special R constant. And so if we change any of these properties, the other ones will adjust so that we maintain that equality. So a changing variable problem, when you're looking at it, you'll see things where maybe you're given 2 temperatures, or you're given a couple of pressures or a couple of volumes, and it's asking, how does the other piece change? Very often with problems like this, you're not going to have an 8 variable problem. You'll know that you're at constant pressure, so that part kind of simplifies out here. Or you'll know that you're at constant temperature. And so this becomes a little simpler. But then you're just solving for what's unknown, and you do not use R in these type of calculations. Okay, but always make sure that you have gases if you're doing anything with either of these sort of equations. Does that help, Sam?
Yeah. So
that's sort of gas law stuff. That's the main stuff that we did with gases. All set, Lauren?
Yes, thank you.
All right, we'll see ya. Other questions? Anything else on gases before we maybe move on to something else? And I want this to be largely interactive so that you guys can ask questions about stuff that you maybe you're feeling fuzzy about. You guys can keep asking. You had said something about like, oh, unit conversion. So, I mean, that was all the way at the beginning, but it becomes an embedded skill. So let's see if we can sort of, well, let me go back here to our kind of our final thing here, right? Where we had some of these questions. You're not likely to see unit conversion stuff in part 1. You're likely to see it individually in part 2. Okay. So let's talk about some classic places where students might make some mistakes when doing unit conversions. There's unit conversions that you have to know, your prefix conversions. So make sure that you kind of, you know, those. Remember, you can bring an index card. So if you're feeling like that's the fuzzy piece for you, put your prefix conversions down on your index card, right? You've got front and back of that index card that you can use. So know your prefix conversions. Like, for example, a meter is 100 centimeters. Classic place that students sort of mix these up is they'll have the wrong pieces. They'll know that it's 1 in 100 for these, but then they'll put them in the wrong spots. So it's one place where students can mess up. So make sure that you have this big little relationship. So the bigger number goes with the smaller unit. Okay, to make sure that you have those pieces in the right spot. So that's a classic place where students can mess up and they'll be off by a factor of 1,000 or something like that. Also know too that if we need to convert, for example, here from square centimeters to square meters, we can put the relationship between meters and centimeters as a unit conversion, but then we have to square the entire thing. So that square gets applied to the unit and the value. So we have to make sure that we do that and recognize that there's 2 100s in the denominator. So a classic place where students can make mistakes there. Okay, so these are some more basic sort of unit conversions. This one has a little bit more strung together. Always remember when you're doing unit conversions to start with something that you know. And sometimes it's confusing because people will not know that it's okay to have something that is not a relationship quantity. You don't have to have a numerator and a denominator with unit conversion pieces, particularly if it's a measured quantity that might just have a single unit with it. And then when you're using unit conversion to change your units, that's often when you use those relationship quantities. But sometimes people get confused because they're like, something has to go above something else. So they'll take something that doesn't have a relationship quantity with it, and they'll just throw something else in the denominator, making it so that it's not. So some common mistakes that people make with that. And, you know, oftentimes you can sort of puzzle your way through unit conversions. If you have a problem, just start writing down the pieces that you have. And it's almost like this puzzle, like, how do I put these things together so that my units cancel? So meters goes away. Kilometers is going to be what I want to have left. Seconds goes away. Minutes goes away. And I'm left with kilometers per hour. So if you're good at unit conversion, you can oftentimes get to an answer for a problem without truly even understanding what's going on if you put those pieces together correctly. Okay. Stoichiometry at its core is unit conversion, right? So we see sort of applied unit conversion. Like these were simple ones where they really don't have anything to do with chemistry, but stoichiometry at its core is unit conversion. Other questions on unit conversion? Sometimes it's sort of like chess sometimes, where you have multiple pieces to go together. You sort of have to see the steps. When you go on, those of you who have to take organic chemistry next year, you'll do what we call organic synthesis steps. Again, it's like stringing multiple things together to get from one place to another. Anybody else have any questions or things you want to ask about with unit conversion? Again, some important things to remember. Unit conversion always comes, when you're doing it, always have a value, a unit, and a qualifier, right? Have three things. Be overly detailed when you're doing things, because that can help make sure that you don't miss an important step that's going to be a numerical piece that can cause you to be off by a factor. What else? Oh, wait. Redox reactions, okay? So we've got the qualitative pieces to redox reactions, which we'll kind of see a little bit here. Let's find some pieces here in part 1, okay, which has to do with thinking about assigning oxidation states. Something you want me to go over there with that? It's like everything with redox, totally fine. Okay. When you're assigning oxidation states, oxidation number is the same sort of terminology. So if you see that, it's referring to the same thing. What we really want to do is understand that some pieces are always going to have the same oxidation state or oxidation number. And we're going to use those kind of as anchoring points to figure out something else. So a couple of things that we have here, 3 out of these 4 are things that are neutral compounds. So all of the oxidation pieces have to add up to the overall charge. Okay. So we always sort of did these in the same sort of format where we kind of write the substance that we have, and then this all has to add up to 0. So I didn't write anything down below, but there's going to be certain atoms that we know have the same oxidation number. Okay, let me go and show you where this is. I'm going to kind of go backwards for a minute here before we come back to this problem. That's kinetics, so I got to go earlier. I wanted to show you where this table is. So it was at the very end, right before gas stuff here. This table, when we're assigning oxidation numbers, okay? So if you go back to unit 4 and look at the notes there, you can find this table. There's going to be certain things that always have the same oxidation number. Those are going to be like our anchor points. We always know we can start with that one. So I just want to run through them right now. Any metals, so things that we find in group 1 or group 2 of the periodic table, are always going to have the same charge, +1 or +2. Okay. Hydrogen is always going to be +1 when it's with a nonmetal. If it happens to be with a metal, this is what we call a hydride, then it'll be a -1, but that's going to be a very specific. You'll see like sodium hydride, NaH. Okay, but most often hydrogen is going to be +1. Oxygen, almost always going to be -2 unless it's in a peroxide compound. And the only one that we've talked about is H2O2, hydrogen peroxide, and then it'll be -1. Okay, so we've got these anchor points. And usually they're based on, like for group 7A, that's the halogens. It's what the charge is if we made it in an ionic compound. Where things get mushy is when they're in the middle of the periodic table, because those are things that can have multiple charges. Okay, and it's going to tend to be those metals that are in the middle or some of the nonmetals that we're going to see on the right side of the periodic table. Okay, so this is where we're going to get that information sort of for those anchor points. So let's go back to that problem that we were working on and kind of see where all of these pieces come together here. So that's why here I know that nitrogen is going to be +1. So that's how I know. I always write oxidation numbers on top. And because, and I can actually go through and I'll write this down below here. I know that the net is going to be +3 because I have 3 of those hydrogens. So now I can say how many, or what's the negative charge that's going to be coming from any of the nitrogens that I have? Well, it's going to be -3. And since there's only one nitrogen, the oxidation number on that nitrogen must be -3. Good with that one? Anybody have questions? Okay, so let's take this next guy. Now we've got an ionic compound here, but it's just asking about nitrogen. So we need to sort of pick this apart. If this question asked about magnesium, it would just be +2 because it's just the charge on whatever metal we have. Now in this case, NO2 is going to be nitrite. So if I come over here, it's NO2 -1, okay? And again, we could either remember and know that nitrite is -1, or knowing that magnesium is +2. If you forgot, since I've got 2 of those nitrites, that's a reminder that NO2 is -1. Everybody good? So now I know that everything has to add up to -1. Okay, so now I'm going to start with things that I know are constants. Oxygen is -2. So since I have 2 of those, so I'm working kind of this way, and then I'm going to work my way up. That's how I'm doing all of these problems, right? So I know that oxygen is -2. I've got 2 of them. So that gives me a -4 charge from those oxygens. Now I know this needs to add up to -1. So here, these were both the same number, just plus and minus. Because this needs to add up to -1, that one's +3. I only have 1 nitrogen, so this nitrogen is also +3. Everybody good? Questions? Where's the muddy point for this? Because I want to make sure I don't keep going through the same thing if you're like, Dr. Kearney, I got this. Got it. Okay. So this becomes a simple skill, right? That will get embedded when we do things like identify who's being oxidized or being reduced. Okay. So the only other things I'm going to say about these 2 problems, keep working through these. And again, the key is posted. If you've got ions, polyatomic ions, the charge has to add up to the charge on that. And this is just giving you a polyatomic ion to begin with. So maybe working through a problem like this next one. Yeah. So determine which element is oxidized and which is reduced. So we still have to go through and do everything that we just did above, but we have to do it for every element that's there, because we have to then ask the question, which element is changing its oxidation number? And that's going to determine things that are undergoing either oxidation or reduction. So taking this first guy, anything that's in its elemental form has an oxidation number of 0. And then we can see over here with sodium oxide, oxygen's -2, sodium's +1. So I can see when we go from 0 to +1, and this is where it can get confusing. When you go from an oxidation number of 0 to +1, that meant you lost electrons. And it's a little bit confusing, like, wait a minute, my number got bigger. How does it, but I'm losing negative things. So when you lose negative things, your oxidation number gets higher. Okay, so that is an oxidation. And then oxygen undergoes reduction. Okay. Oxidation, if you're Leo Gur or oil rig, whatever mnemonic you want to remember, and again, you can write that down on your card if you're feeling like redox stuff is fuzzy for you, but that's going to allow us to recognize that sodium is oxidized and oxygen is reduced. Noting here that it talks about, tell me the element that's oxidized or reduced. Okay, so if you wrote down something that is not the specific element, you would not get credit for this problem, because I need to know what element that's happening with. Other questions that were, because we really didn't do too much more, I don't think, with this. We will get to next semester, like how we balance redox reactions when we learn electrochemistry, but we just sort of had an introduction here to just understanding how to assign oxidation numbers and understanding what's being oxidized or reduced. Anybody want me to go through another problem with this or make sense? Okay, what else?
Can you do like the salt base equilibria?
So what kind of equilibria?
The salt base.
Salt-base equilibria. Okay, so let's see if we have any like problems here. So sometimes you might see a problem, looking at problem 19 here, where you might have a salt, where I'm asking the question, is the pH of that salt solution going to be acidic, basic, or neutral, right? So that's where you have to recognize that you have a salt, pick it apart into its pieces, and then say, well, what's going to happen here? This one actually doesn't have a salt with it. So scratch that with giving an example here with this guy. So that you might see some qualitative stuff, right? So remembering that in general, unless you have an ammonium salt, you're generally talking about something like sodium or potassium with a conjugate base of a weak acid. So most salt solutions that we've seen are going to make the solution basic because the acid base character is going to come from that conjugate base piece. I'm talking with my hands, but does that make sense with what I'm saying? Now, notable examples would be if you have an ammonium salt. Let's take ammonium chloride, NH4Cl, right? I put those both in solution. The chloride does not contribute anything to acidity or basicity, but that NH4 plus, once it's in solution, its option is to find water and give a proton to water, meaning that it's going to make the pH lower. It makes the solution acidic. So that's one of the salts that will make our solution acidic. The other ones that can make our salt solution acidic is if we have highly charged metals. So for example, if you had iron chloride, FeCl3, let's say, that's an iron 3+, that's going to make this solution acidic. But a lot of the salts that you're going to see, if they've got sodium or potassium with it, that means they've got an anion with it. That maybe is the conjugate base of a weak acid. And if that's the case, it makes the solution basic. Does that help with those qualitative pieces? So I think there's probably a problem here. Let's look where we could do sort of a computation with it. Okay, this is an example. Well, this one's not a salt. So let me go to a place where I think is going to be a good opportunity just to kind of do some review of things when we're thinking about salt solutions. Because one of the things I noticed is that there's many people that I know studied really hard for problems like that. And then I talk about the places where you could make a wrong turn because you forget to do this. And then some people made that turn when they weren't supposed to, right? So that's sort of some easy mistakes to make. So let me find a couple of slides here, which I know will be helpful to help us think about this. So this was our salt stuff. So this is what so when you have to make a pH or determine the pH of a solution, right? Here's your checklist for things to go through, and highlighted are places where students make wrong turns, and highlighting that sometimes people would make these turns when they weren't supposed to. So again, put your substance in water, eliminate spectators, and see what you have. Then write an equilibrium equation for the right chemistry. Do you have an acid in solution or do you have a base in solution? So let's take a salt, for example. Let's take, say we have like sodium acetate. I'm going to abbreviate acetate, OAC. So when we dissolve this in water, we know we're going to get sodium cations and then acetate anions. Spectator with sodium. So this guy, we have to say, what is the acid-base chemistry that can happen? And so the acid-base chemistry that can happen is we can have this guy find water, and it's going to generate acetic acid and then leave behind hydroxide. So it's really important that you write your initial equation correctly, because otherwise you're not going to have the right equilibrium constant and so forth. So if this was a problem that we were doing, just kind of walking through, and I'll find an example here in the problems that maybe we were working on in class, is we would have to choose a KB for this. So this would be a base problem, right? Because we wrote a base equation. So we need to use KB. And if we do our ice table here, and this is going to be plus X, our X is going to be equal to hydroxide concentration, which means we're going to have to go around the block to determine pH. So does this help, or can I answer any, that's sort of very general. I'm going to look at a problem in a minute, but does that help? It's super, and I know it's frustrating because if you start out with the wrong equation, it's almost like we're doing like I put a blindfold on you and spun you around in circles, and you like, I think I know what I'm doing, and like you're heading off in like the opposite direction you're supposed to, because, and Sam's nodding, I know, because that happens. It's easy, super easy to do. So and sometimes, and I know you did this on the quiz that we had, where it was maybe an easier problem because it was a weak acid problem. And you guys were like, she's going to give us a salt problem. She's going to give us a super hard one. And then you kind of like went around the block in circles, and nope, it was straightforward. Yeah. So look at what you have and then make sure you are doing the right equation. So even if it's as you're practicing and studying, there's flashcards for salts that are like up on Blackboard as a group. And that way you can sort of cross-check yourself if you study with somebody else. Like, say, if this were to dissolve in water, what would the equation look like? You know, what would my ice table look like? You don't need to go through and solve the whole thing, because solving that is going to require that you know the concentration of that species in order to put into your ice table, but you can at least make sure that you've set it up correctly. So sort of practice with, there's weak acid, weak base, and salt flashcards that are online. So particularly if that's something you're struggling with, take a few of those and practice with a group so you can sort of cross-check yourself and make sure you got the right equation, because that's usually where people make a mistake. And then they do the rest of it right. So you'll get some credit, but you kind of make a wrong turn. Does that help? Do you want to look at a specific problem, or?
I think I'm fine.
Good.
Yeah.
Maddie. What's that?
What year?
This was 7. Yep. Because the latter half of the course, so let's like split up the course in half. The first part of the course was, we had, you know, our introduction to chemistry. We did some unit conversion. That was the big thing from unit 1. Unit 2 was naming. And then we had kind of some basic nuts and bolts about, you know, atoms and making molecules, learning how to draw some basic structures. Then we had stoichiometry in unit 3. And then unit 4 was learning about our main kind of chemical equations. And then we tacked gases sort of on the end of that. And we really weren't into too much deep math on that. Maybe there was kind of an involved unit conversion problem, but for the most part, you know, we didn't have problems computationally that took a long time. And then we came back, and then the last 4 units were kinetics, equilibria, acids and bases, which is really a kind of equilibria, and then complex aqueous equilibria, which are buffers, titrations, and then our sparingly soluble salts. So of that sort of broad strokes overview, what is fuzzy?
The kinetics problem where you have to do half-life and like when they're all together in one problem.
Okay. So kind of giving a summary of sort of kinetics. So before I kind of pull something up here, when we think about kinetics, right, there was kind of writing a rate law. So let's just kind of take a quick look at, you know, before this. I'm just going to kind of flip through slides fairly quickly so we can kind of see the concepts that we had with kinetics. Doesn't help. Gosh, once your eyes get to be above like age 48, like this is way too small for me. And I'm like, I think I'm sort of seeing where I'm at, but all right, so kinetics. Oh, I think this was reviewing for exam 3. So let me go back a little bit. Sorry, I'm trying to find just kind of our notes so we can sort of summarize. That was equilibria, so it was before this. Here we are. Okay, so 3. All right, 2. And then here was, okay. So first part was writing reaction rates and rate expressions. Okay on that? Okay, so just to kind of zoom through some slides really quick, this is where you had to kind of write a rate as a function of both reactants and products. You can write a rate expression with respect to both reactants and products. Disappearance of reactants, appearance of products. So that's a positive there, right? Everybody good? It's just kind of doing a rapid sort of review here. Then we can use the rate expression that maybe we're given the rate of something and we want to relate it to the rate of something else. This is almost kind of like a stoichiometry problem where we're relating two different things, but we're going to use our rate expression as a way to relate those. The biggest mistake that students make with this is when you're given a rate, they just put it in for this whole thing. And you can't do that. It only goes in for this part. You still have to multiply it by whatever the fraction is. So that's a common place where students make mistakes on that. And then you're solving for whatever I've got boxed over here in green, which is the rate of something that's unknown, but you still have to make sure you keep that fraction. So those fractions are separate from whatever you're calling rate. That's the biggest mistake that students make on problems like that. So that was writing and using rate expressions. And then we had, I think we had an exam there in between. So then the next thing, and I think, Kayla, this might be getting at your question, like using those, what we call integrated rate laws. And so we learned about first order kind of reactions using nuclear decay. So that was sort of this problem. So in unit 2, that's where we learned how to write nuclear equations. We can go back and look at that in a minute if everyone's like, oh yeah, writing those nuclear equations. You're going to have a nuclear equation that you're going to have to write. But nuclear decay is a specific first order example. Okay, so just looking at some of these problems, you can have like nuclear decay processes that are first order. You can also just have a regular old chemical equation that's first order. But we have to know that it's going to involve this equation and then this equation. We have 3 different flavors of what we call the integrated rate law. Don't waste space on your index card writing down equations, right? That's why you have that, the first 2 pages, so you know what's provided for you, okay? So don't need to waste time putting equations down on your card because those are provided. But you need to know which of these 4 variables we're solving for, how much you start with, how much you have now, how much time has passed, and then rate constant, that's a constant, but you might have to use an equation like this to convert a half-life that's given to a K value, okay? Places that become challenging for students with these kinds of problems is maybe I'm asking the question, how much has reacted, right? And that can be confusing because that's really the difference of these, n sub 0 minus n sub t. So if I talk about how much you start with, how much you have left, the difference between those is how much has reacted. So make sure that you're answering the prompt correctly. But let's see. So we did a few problems there. Oh, come on. There we go. Then we got to do rate law, reaction order, and rate constants. Okay, so I think it's coming after this is where we have the other sort of integrated rate laws. So make sure that you know, and one of the things too is as you're studying, and maybe even if you're just looking over the key, if you didn't have time to do all the problems kind of on that practice sheet, make sure that you would be able to say, if I'm looking at this problem, here's how I know that I'd use this equation or this strategy, right? So when you're doing rate law, reaction order, method of initial rates, right? This is where we're going to be seeing like tables of data, and you're asked to write a rate law, right? Hopefully this might be something too that you guys got a lot because you got it in lecture and labs. So it might be something that's a little bit kind of more crystallized in your brain because you saw it in multiple places, but that's that method of initial rates. And Kayla, to get at your other question, okay, then we moved on to thinking about the other integrated rate laws, which were basically looking at all of these equations. So how to do these problems, right? You have to choose the right equation. make sure that we have to get to K. So if you have a half-life that's provided, you'd need to use the corresponding kind of half-life equation. And again, making sure that you solve for the desired variable. So does that help, or is there anything else? Question? Okay. And with so many of these problems, the level of difficulty depends on how easy something is provided for you. Okay. And I will say, I don't think you'll be surprised by anything on parts 1 and 2. It's going to look very similar to the scope of questions that you've seen on these practice ones. Okay. The last 3 problems, but they're only 10 points each, are can you put together kind of pieces, you know, no context for where this is coming from and so forth. But again, you get to pick out of the list of possible, I think there's 10 questions, you pick three out of them. Anything else on kinetics that people have questions on sort of while we're in this space? So again, kinetics is this piece that we really haven't thought about much. Equilibrium usually is fresher in people's brains because we had like 3 separate learning units on equilibria. What else? Allie? Yep. So let's go look at, because again, some of these things too that were a little bit like distant from, and we haven't applied them. So that was looking at writing nuclear equations, right? Maddie.
Do you want us to specify that alpha is helium, or do you just write it as alpha?
You can just write it as alpha. Yep. Nope. So let's pull up this sheet that's right here. Okay. So this is something not provided for you, right? Stuff you need to know. But again, you guys can pick what's the stuff that's going to be important for me to put on my card, right? You need to know what these particles are and what they're abbreviated by. So to Maddie's question, it doesn't have to be that it's helium 2+. You can write alpha, okay? But it might be more helpful if you write alpha 4-2, because that helps you remember what you're doing with those numbers. If you just write alpha, you might miss that. I got to do something with that 4 and that 2. But to Allie's question, electron capture, part of what the challenge is with these problems is figuring out where reactant side or product side things go. Okay, so and I think I've got some hints here. Common mistakes that students make is not putting things on the right side. So when you see that it's talking about something that's emitted or it decays or you have alpha decay, that means you're putting those pieces as products. Okay, if you hear words like bombarded with, that means that part is a reactant. So an alpha particle isn't always a product. If you say it undergoes alpha decay, yep, it's a product. If you say an alpha particle is emitted, yes, it's a product. If you say bombarded with an alpha particle, that alpha particle is a reactant. So you'll have language in the prompt that's going to tell you sort of what that is. So Allie, to your part, electron capture is always a reactant. So that's looking. Hey, Kyle. I don't know if he'll hear me. He was stopping to pick up something. Electron capture is always something on the reactant side. Okay, so that's usually the piece that's challenging, Allie, is making sure you get things on the right side. And then sort of looking at making sure that all of your pieces add up. Classic places where students make mistakes too is if you're talking about something that has a minus charge in that lower part, you have to make sure that you do your math right. Okay, that's going to cause an increase. If you're talking about beta decay, this is going to cause an increase in the atomic number. Okay, does that help, or do you want some more? So you're going to see a nuclear equation that you're going to have to take words and write it into kind of what's going on. Other stuff. Chloe, did you have a question? 7.4. Help me out with what that is. You're not going to see too much with that. No, it's really qualitative. Like I would expect you to be able to understand that if anything, it's something that just helps us understand, for example, that HClO4 is a strong acid and HClO is a weak acid. and we can rationalize that, but you're really not going to see much on the final exam. I don't know. You're not going to see anything on the final exam about that. Okay. What else?
I saw on the study guide, some of them using ICF table, and I was really confused on why. Like, it seemed like some of them wouldn't need to use an ICF table.
You might not need to. You might be able to do it in your head. ICF table is just a bookkeeping method to keep track of chemistry that's happening.
Okay.
So if you can figure out what's going on, I just tend to always do them because if somebody's looking at the key, it's an easy way for them to understand and keep track of
Okay.
things that are appearing, things that are disappearing. But you're right, you don't always have to do them.
Okay.
But I also teach ICF tables because at some point we moved to ICE tables, so it's an easier transition to sort of have that format for how you think about keeping track of things. What else? My plan was to only be here about an hour today anyways. I'm like, I don't think we have the bandwidth to talk about chemistry for 2 hours, so. What, nothing else that's in your. I was gonna try to open up the, yeah, don't look at my desktop.
There's a lot of emails.
Oh, it's so funny where people's eyes go to. That's my Gmail. Like my Gmail is like the garbage stuff. Like, what is it at? Like 52. It's God, it's just like garbage, tons of garbage. But when like I have to give an email, like when you're at the grocery store or whatever, yeah, that's what it is. Oh, let's see. Final exam study guide. I just kind of want to, oh, nope, wrong class. Nope. Oh, I know. Oh God, you want me to click on that, don't you? Not going to happen.
Like 2 seconds.
No, because this is being recorded and people will pause it. I know how you guys work. I could, yeah. Oh, but actually, I think this is most of you. That's true. I know that they, I was trying to get to I probably can get to it via Blackboard. I just wanted to open up the study guide and just see if there was anything else that I wanted to. No, and it's funny, like Dr. Brown is much more math oriented than I am. So he loves like set it up or do no. Yeah, on the practice. So
Yeah, try to do the math. There were people like that hadn't had lecture for that topic yet. And they were like, what are you doing? And it was just strange. You're like, when we already learned it, I was like, oh my God, what's that?
Yep.
I just don't really discuss it.
Well, and it's like different people have different ways, and that's why it's always challenging. Like if you guys go to YouTube and you find a different way, sometimes it can end up being more confusing because it's a different way, and if you don't recognize it, you're just going around the block a different way. It can end up making things more confusing. All right, so yeah, I'm just going to do in the last 10 minutes we have here, just kind of a quick overview of and highlighting things that are important, right? Unit conversion. Make sure you know how to do unit conversion. Naming compounds, and you guys saw some examples of kind of this earlier stuff, whether it was sort of doing isotopes and figuring out those things, naming compounds, drawing compounds. You guys good with sort of like the basic drawing compound sort of piece? Keep in mind that some of the problems at the end might be things where they're kind of combining skills. Most of the stuff in parts 1 and 2 are what I'm sort of calling single skill type problems. The problems at the end are ones where you have to pull stuff together. You know, you might have a chemical structure that you have to draw at the end based on some data that you get from, you know, figuring out an empirical formula or something like that. So kind of putting pieces together. Stoichiometry was kind of the big thing. Everybody's probably done a lot of practice with limiting reactant problems. Okay. Again, chemical reactions. We did some very basic stuff with precipitation reactions in unit 4, but then we elaborated on that when we did our last sort of skill on sparingly soluble stuff. We did some gas chemistry stuff, redox chemistry. We went through kinetics. Big picture thing with equilibria too is make sure that you get back into the habit of looking at your balanced chemical equation, because we spent so much time doing things where like all your X's were just had ones in front of them because that's what our acid-base reactions or things were. So make sure you remember to be using your balanced chemical equation with the right coefficients. Acid-base equilibria, right? We had some good questions about how to think about, salt problems. And to Chloe's point, don't really worry about the trends in acidity piece. I do want you to know, like, if you're looking at a molecule, which proton would be the one that comes off, okay? And if you had to make a conjugate acid or a conjugate base or determine protonation state, that's sort of related to this piece. But don't worry about the Lewis acid stuff. And then our last learning unit, it's probably the freshest in your brain, but it's really just applied equilibria. Anything else?
Sure.
Don't be scared. Don't be scared.
Yeah.
And you have the backside of your note card too.
I folded it in 4s, and then you have 4 quadrants on each side, and then.
Oh.
More. Yeah.
Oh, I like that idea. So you have basically all 8 units.
Unit 1, I didn't really have much, so I extended unit 2.
All right.
I know how to do it. I just need to take a quick look at the study guide and then. I don't know why it's just.
Just worry about single problem.
No, like, I do.
Thing to do with.
And I could make a boatload of money if I could figure out how to create, like, fix that disconnect, because that gap is big with it's like, once you know what to do, you guys are good. Right. But like, I literally just spin you around in a circle and I put you in the middle of the floor and it's like, go. And if you start going in the wrong direction, like, you know how to go, you know how to do that wrong direction thing, Sam. Yes, I know, right? You know how to do that wrong direction thing, but you don't know that you're going in the wrong direction.
Exactly.
And I don't know how to,
It's like if you can't do this, but it's like a heading above it. You're like, this is a.
yes, I know.
You can't do that.
And I feel like that is the challenge when you're studying things like in these little islands, so that you know the island that you're on. But the final exam, especially, I'm like literally just dropping you in the middle of the ocean. You don't know which island you're supposed to swim towards. Right. And it's like, I think you guys are probably good where it's like, you're not going to start drawing ice tables when it's kinetics, but that I have seen that, right? Where students don't understand, like, this is kinetics, not equilibria. Right.
That's like where the line is at. It's like, I know how to do everything, but like when I look at a problem, I'll think it's something else.
Right.
So,
Or
like, if the exam went in order, I would.
right.
Like,
Or I will say, I noticed this on the lab final, right? Dr. Brown, because he sort of did this latest version of the lab, but you guys all had, we're not gonna talk about the lab final. This is not a problem to say this, but it does say like lab number 1, lab, it says,
That's what.
it does say what lab it came from. So I think that sort of helps put it in context. But Hannah has not taken the lab final yet. She's taking it tomorrow, so can't talk about details of the final.
Oh my.
It's like study the sheet.
And if you know how to do the
You showed it. Oh, yeah.
the review guide for it. And if you know how to do the calculations that you did for the lab,
But that's the other thing.
I'm going to stop this now.